So far, we've talked about equilibrium constants as something that's occurring at equilibrium. And so I want to take a moment to talk about, well, what happens when you're not at equilibrium? And how do you know if you're at equilibrium or not? Especially if you have information about the concentration of reactants and information about equilibrium, and how do you compare? So what we use is the reaction quotient, which is Q instead of K. Here's the thing about the reaction quotient. It's exactly the same expression as the equilibrium constant expression. So it's still the mass action expression. And at any point in the reaction, you can calculate that ratio of products to reactants, and it will be Q at any time, except when it's at equilibrium. And that's when it becomes K. And so really it's this ratio right here that we're looking at of the mass action expression. It's going to allow us to decide which way the reaction's going to go if it's not quite at equilibrium to reach it. And by that, I mean, will more reactants form to reach equilibrium, or will more products form to reach equilibrium in a ratio, right? So we'll just make a quick note here. And so when you're working on calculations for the reaction quotient, treat it exactly as the equilibrium expression, K, and just use that Q value, or if you read about something referring to the quotient, just know that we're talking about a reaction that we don't know is at equilibrium yet, or is not at equilibrium. I like looking at these with a graph. This one I really think is helpful. So on this graph, this red line right here is representing the equilibrium constant. So this is K, which means we're at equilibrium. So if we calculate the ratio of products to reactants, we'll be calculating the reaction quotient if we're not at exactly that point. And so we're looking at just kind of a basic A for reactants, B for products right now. And we're told that our equilibrium constant is 1.45. So that's right here. So if I have a ratio of reactants to products that is going to be less than the equilibrium constant for the reaction, then that means that to reach equilibrium, I'll be forming products and reactants at the same time, but I'll be creating more products than I'm creating reactants. So that way I have this kind of like macroscopic picture of more reactants and more reactants and more reactants forming over time. And until I hit equilibrium, and then those rates of the forward and reverse reaction will be the same. And I'll have reached that ratio of 1.45 for products to reactants. And I won't see change beyond that. Now, if instead I calculate the quotient and I have a number that's larger than 1.45, that means that I still need to form more reactants relative to products before I reach equilibrium. And so we'll see in this case, kind of this net macroscopic picture where we're forming more and more reactants, even though we're forming both reactants and products at the same time. And until I hit that 1.45 number for the ratio between the two for this specific reaction, and I'll see then that the reaction appears to stop, or the concentrations appear to change. And so kind of the key ratios to kind of keep in mind. So this blue one that, so our Q is larger than K is right here. The reaction will proceed fastest in the reverse direction is the other way to say that. So that rate of the reverse reaction is a larger rate than the forward reaction. I'll see the larger accumulation of reactants relative to an accumulation of products. And our first one that we said, when our Q is less than K, that reaction is going to proceed fastest in the forward direction. So we'll have a faster forward rate, which means I'm going to see this net accumulation of products on this macroscopic level rather than reactants. Now, once Q equals K, then you're just at equilibrium. And that's this line right here, that K equals 1.45. So if I have some information about our A and B, and I know the concentrations at a moment, I can find out if we're at equilibrium. So our first one, we'll just calculate it. We'll call it Q because we don't know if it's at equilibrium. Maybe it is, then we'll switch it to K. will be equal to the concentration of B over the concentration of A. I'm getting that right here. That's because B is representing products. So this will look like 0.25 molar divided by 0.75 molar, which will give me a value of 0.3. So that 0.3 is less than my K value, which is equal to 1.45. Therefore, the forward rate will be faster than the reverse rate. Let's look at another example. If we kind of switch this around and A is the lower concentration and B is higher. In this case, Q is going to equal still the concentration of B over A. So we'll have 7.5 this time over, or sorry, 0.75 over 0.25, adding extra zeros everywhere. And we're going to get a value that's equal to 3. Well, 3 is greater than K, which is equal to our 1.45. And so we can see that the reverse direction, the reverse reaction rate will be higher than the forward as we accumulate more reactants to reach equilibrium. So this could be a really helpful tool for trying to determine where a reaction's at if you're following a reaction by concentration, and allowing you to predict if it still has quite a bit to go in terms of time before it reaches equilibrium or if you're basically there.